Everyone is afraid of uranium for the wrong reason. You picture the mushroom cloud, the glowing green rods, Chernobyl. That's what they showed you in school. And honestly, I understand why. Those images are dramatic. They stick. But none of that is what kept me awake in my laboratory. What kept me awake was something quieter. Something that had no right to be happening at all. Uranium was sitting there, not burning, not reacting, not being struck by anything, and it was producing energy, continuously, spontaneously, with no source I could point to. Everything I had been taught said that was impossible. You want to produce energy from something, you burn it, you heat it, you apply force. That's chemistry. That's physics, as the 19th century understood it. Matter doesn't just radiate, not on its own, not forever. And yet, here was this gray, dense metal, unremarkable to look at, and it was doing exactly that. I could measure it, I could verify it. I could press a sample against a photographic plate in complete darkness, and it would leave a mark, not because of light, not because of heat, because of something coming from the atom itself. That's not a chemical reaction. It never was. And the moment I understood that, truly understood it, the entire framework I had built my scientific thinking on began to crack. So if it isn't chemistry, what is it? I want to tell you honestly how this discovery actually felt. Because the way it gets taught, Becquerel sees a glow, Curie measures it, science advances. That's the cleaned up version, the heroic version. The real version is messier and more interesting. Henri Becquerel noticed in 1896 that uranium salts were fogging his photographic plates. He thought it was fluorescence, that the uranium was absorbing sunlight and re-emitting it. That was a reasonable guess. A wrong one, but reasonable. What I found, when Pierre and I started measuring systematically, is that the intensity of the radiation depended only on the amount of uranium present, not on its chemical form, not on temperature, not on temperature, not on temperature. That was the key. That was the crack in everything. If it were a chemical reaction, it would depend on the chemical environment. But it didn't. The radiation was coming from the atom itself, from something inside it that had nothing to do with how the atom was bonded to its neighbors. I named the phenomenon radioactivity, and here is the honest thing I need to tell you. I named it before I understood it. Naming something is not the same as explaining it. I measured it with precision I was proud of. But what was actually happening inside that atom, I did not yet know. The 19th century's most confident belief was that atoms were permanent, indivisible, stable. The Greek word atom literally means uncuttable. That was the assumption baked into every equation, every experiment, every theory. What uranium was doing was transforming, quietly, continuously, without permission from any law of physics anyone had written down yet. Imagine a brick in your wall, solid, fixed exactly where you put it. Now imagine that brick is, at this very moment, slowly becoming a slightly different brick, releasing a tiny pulse of heat as it does, and that nothing you do, nothing you say, no force you apply, can stop it or speed it up. And it's been doing this since before the wall was built. That's what matter was doing. That's what matter is doing. The universe, it turned out, had a secret metabolism, and we had been calling ourselves physicists without knowing it. So let me show you what's actually happening inside the atom, because this is where it gets genuinely strange. At the center of every atom is a nucleus, protons and neutrons, packed together in a space almost incomprehensibly small. And inside that nucleus, two forces are fighting. The first is electromagnetism. Protons carry positive charge, and like charges repel. So every proton in the nucleus is pushing against every other proton, all 92 of them, in the case of uranium. That's an enormous amount of repulsion, compressed into an almost impossibly small space. The second force is what we now call the strong nuclear force, at very short ranges, shorter than the width of a proton. It overwhelms electromagnetism. It binds protons and neutrons together with tremendous strength. It's why nuclei exist at all. Uranium-238 has 92 protons and 146 neutrons. That's a heavy, crowded, slightly ungainly nucleus. The strong force is holding it together, but the electromagnetic repulsion is always pushing back. The nucleus isn't sitting still, it's vibrating, flexing, like something that's been compressed slightly beyond its comfort. And occasionally, in uranium's case, very occasionally, the repulsion wins a small battle. The nucleus ejects a tightly bound cluster, 2 protons and 2 neutrons, moving fast. We call this an alpha particle. You might recognize it. It's identical to a helium-4 nucleus. After that cluster leaves, the atom that remains is no longer uranium. It has 90 protons now. That makes it thorium-234. A completely different element. That transformation is real, permanent, and irreversible. The energy released in that event doesn't come from a chemical bond breaking. It comes from mass. The alpha particle and the thorium nucleus together weigh slightly less than the original uranium nucleus did. That missing mass, a tiny, almost unimaginable sliver of it, becomes kinetic energy, pure motion. This is Einstein's equation, E equals mc squared, not as a chalkboard abstraction, but as a physical event happening in rock, in soil, in the ground beneath your feet, right now as I'm speaking. This isn't a metaphor. Uranium in the Earth's crust has been doing this for billions of years. It's doing it at this exact moment. Now, here is the part that nobody talks about in school. The part that, when I think about it even now, makes me sit with a kind of quiet vertigo. We know that every uranium-238 atom will eventually decay. We know that if you have a large sample, half of the atoms will have decayed in 4.5 billion years. That's the half-life. That's a measurable, reproducible, reliable fact. But we cannot tell you when any specific atom will decay, not because our instruments aren't sensitive enough, not because we need a better theory, because quantum mechanics, our deepest, most carefully tested description of reality at the atomic scale, says the decay event is genuinely, fundamentally random, not pseudo-random, the way a coin flip seems random because we can't track every variable. Truly random, undetermined, even in principle. Think about that coin analogy for a moment. You have a coin that, on average, will flip heads once in 4.5 billion tries. You know that with certainty, but each individual flip, you can say nothing about it. Not probably heads, not probably tails. Nothing. The outcome does not exist before it happens. That's not a gap in human knowledge. That's a gap in the structure of reality itself. I spent my life measuring what I could measure, developing techniques, building instruments, isolating isotopes, filling notebooks with data. Precision was my discipline. It was my comfort. This is what I could not measure. And this is important. It is what no one can. Not because we haven't tried, because trying isn't the issue. The randomness is not something hiding behind our ignorance. It is native to the fabric of what is. The idea that every event has a definite prior cause, causality as we intuitively live it, quietly, completely breaks down at the atomic scale. An atom decays. There is no cause. There is only probability. I find that humbling. I think you should too. Let me pull back now. Let me show you something larger. Uranium did not form on Earth. It couldn't have. The temperatures and pressures required to fuse nuclei as heavy as uranium exist only in one place, a dying star in the final moments of a supernova explosion. The uranium in Earth's crust was forged in a star that no longer exists, a star that collapsed and exploded before our solar system was born. The debris, including uranium, scattered through space, and some of it became the material that eventually clumped into our planet. So uranium arrived here with the Earth, and it has been decaying ever since. That decay is not just a historical fact. It is an ongoing process with consequences you live with every day. The Earth's interior is still hot, not mostly from the original heat of formation that would have dissipated long ago. The reason the core is still molten, the reason plate tectonics still operates, the reason volcanoes still erupt, and the magnetic field still protects us from solar wind. A significant part of all of that is powered by the radioactive decay of uranium, thorium, and potassium deep in the Earth's mantle and crust. The ground is warm beneath your feet because of radioactive decay. The magnetic field wrapping this planet, making complex life possible, maintained in part by the same process I was measuring in my laboratory in Paris. And then there is this. Right now, in your body, there is radioactive potassium-40. It's in your muscles, your blood, your bones. It got there because you ate food, because you drank water, because potassium is essential to life, and a small fraction of all potassium is radioactive, always has been, always will be. Your body produces approximately 4,000 radioactive decay events per second, every second, while you sleep. While you're sitting here watching this, you are not observing radioactivity from a safe distance. You are part of the process. You are doing it. I want to be clear. This is not a reason for fear. Your body has been managing this since the first humans existed. The doses involved are small, and your cells have mechanisms, imperfect ones, but real ones, that deal with them constantly. This is not danger. This is inheritance. You received this from a star that died before the Earth existed. It flows through you right now. It connects you to the origin of the elements themselves. So what are we actually looking at when we look at uranium? We're not looking at a fuel. We're not looking at a weapon. Those are things humans made uranium into. They're not what uranium is. What uranium shows us, what radioactivity shows us, when you follow it all the way down, is that matter is not static. Matter changes. Spontaneously, irreversibly, without external cause. The universe has a direction, a before and after, an arrow. Every atom of lead that was once uranium is a record, a time stamp, a physical inscription of elapsed time. You cannot take that lead and run the clock backward. The decay went one way, and it always will. Here's the question that hasn't been answered, not by me, not by anyone who came after. Why does decay only go one direction? The equations of quantum mechanics are, in a technical sense, reversible. And yet the physical process never runs backward. Why? And the deeper one, why does the universe tend towards simpler arrangements at the nuclear level, heavy atoms breaking down into lighter ones, while tending toward more complex arrangements at the biological level, simple molecules assembling into cells, cells into organisms, organisms into minds? Those arrows seem to point in opposite directions. What connects them? What governs them? Schools taught you uranium is something to be afraid of, or something to be harnessed. What governs them? Schools taught you uranium is something to be afraid of. I understand why those are practical concerns, and they matter. But uranium is also evidence. Evidence that reality is not finished. That the ground rules we think we understand keep revealing new flaws beneath them. That the universe is doing something, transforming, decaying, building, complexifying, and we have barely begun to read what it's actually saying. I did not leave my laboratory with answers. I left with instruments I had built, and a phenomenon I had named, and a certainty that what I was looking at was far deeper than I had originally imagined. I did not find answers. I found better questions. And I think after all of it, after all the years and the measurements and the Nobel Prizes and the notebooks full of data, I think that is the more honest thing to offer you. Not a solution, a direction. Keep looking.